Huh? How much? How much? Zoology. Commerce. Zoology. BCom.
Chemistry. Botany.
Arts.
Must. So up to, have you any idea? I'm getting down to any 9th level. Okay. Okay, shall I start?
Yes, sir.
Okay. So we have discussed yesterday conservation laws, and I told you that some physical quantities remain constant in time, and they are called as conserved quantities. They are called as conserved quantities. These in physical quantities we have force is a physical quantity. I told you yesterday. Similarly, energy is a physical quantity. Your linear momentum is a physical quantity. Similarly, your angular momentum is a physical quantity. These are all physical quantities. These physical quantities remain conserved or constant if no external force is acting on it. If no external force is acting on it, that means we are treating as isolated bodies, isolated bodies, where the external force is zero. External force is zero. So these physical quantities are having deep relation with symmetries of nature. I will be discussing it later. Yesterday we have gone through what is the conservation of linear momentum. I told you that conservation of momentum, linear momentum is basically the quantity of motion possessed by a body, as I discussed many examples. For example, a body having some mass, say a truck having mass, and it is moving with some velocity. Its momentum will be obviously larger in comparison to the momentum of a cycle, because the mass is very small and it is moving with some velocity is lower than that of the truck. So this is the momentum of what you call this bicycle. So if you look at what will happen, linear momentum before and after collision remains constant in elastic collisions. So if two bodies collide, their linear momentum before collision, that means momentum of body A and momentum of body B before collision remains same as the momentum after collision. It may be transferred from one body to another. Truck may transfer its momentum if it hits a bicycle to the bicycle, but overall the total momentum will remain conserved before and after collision. Same was the example with the gun. The gun requires to conserve the linear momentum, because before the firing of bullet from the gun, both bullet and the gun are at rest, and the momentum is zero. Then after the bullet is fired, the gun recoils back, so it compensates for the momentum that has pushed the fire to move forward. So in that way, the momentum again becomes compensate or zero. The total momentum becomes conserved. Then we have gone through the conservation of energy, and I told you that energy can neither be created nor destroyed. It can be only transferred from one form into another form. For example, you are in a shooting star. Shooting star, once it gets collided, it strikes the atmosphere, you can see a streak of light coming out of it. That means a part of energy is being converted into light. It is being transferred from one form to another form. Okay, this was the conservation of what you call the energy. Then or the energy of a freely falling body. At this point, the energy of this the potential energy is if it starts falling, the potential energy goes on decreasing. But kinetic energy goes on increasing. If it falls on the ground, at the ground the kinetic energy will be maximum, but potential energy is zero or minimum, because potential energy is mgh. Height is, there is no height with respect to this ground, here table with respect to this table. So the height is zero, so the potential energy is zero, but kinetic energy is maximum. Similar is the case with the oscillating pendulum. So this pendulum oscillates like this, then comes to its mean position, throw mean position to this extreme end, then again returns to mean position. That is one oscillation. So at extreme position, the potential energy is maximum. Between extreme position and mean position, the potential energy is there is partially potential. The energy is partially potential and partially kinetic. When it reaches the mean position, the potential energy is minimum but kinetic energy is maximum. Similar is the case with other extreme end. Greater potential energy this extreme end. At middle between the mean position and the extreme end, you gain half potential, half kinetic. When it reaches to your mean position, again the potential energy goes on decreasing until minimum and kinetic energy is maximum. This was all about conservation of energy. Then we have discussed it, conservation of mass energy. Conservation of mass energy. Mass and energy are basically interconvertible. You can convert mass into energy or energy into mass. That is given by what you call the Einstein's famous relation E is equal to mc square. mc square. Basically, mass is also a form of energy. This equation says mass is also a form of energy. This is the basis of your atomic and nuclear bombs. Because there you are having a mass, you get a mass defect. That mass is being converted into energy. For example, in case of fission, the energy released is around 24.7 million electron volt. That's a huge energy. Okay. So this was mass energy, this conservation. Then we have gone through this angular momentum. Angular momentum also it remains conserved. It remains conserved. Okay. And we have got, so if torque is zero, your angular momentum is conserved because your torque is dl by dt. dl by dt. If torque is zero, your angular momentum. Yesterday I have already written this relation. Tau is dl by dt. If torque is zero, your dl by dt. So you integrate this, so you will be having dl is equal to 0 dt. Then you integrate this, L is constant. Your angular momentum remains constant. I have quoted many examples of ice skaters, how their spin goes on increasing when they stretch their arms. When they stretch their arms, because the moment of inertia goes on decreasing at that point. When they open the arms, the moment of inertia increases because the distance from the axis of rotation is large in comparison when the skater closes his arms. So these things have been already discussed. But now today what we have to discuss, these conservation laws have deep relation with symmetries of nature. With symmetries of nature. First is we say that homogeneity of space. How we relate the symmetries of nature with conservation laws? We are having what we call as homogeneity of space. Homogeneity of space, that means uniformity of space. Or I can write down uniformity of space. Uniformity of space. That means if you perform an experiment in space at one place and you repeat the same experiment at some other place in space, you will get the same result. That is called as uniformity of space. Or homogeneity of space. Homogeneity of space. Something, the space remains something same everywhere. Same, okay? So we call it as uniformity of space. If you perform an experiment, you are doing some experiment at one point in space, you repeat it the same experiment at some other point in space, you will get the same result. Or at one place, you are repeating the same identical experiment under same conditions at some other place, so you will get the same result. We call it as homogeneity of space. And the second thing is we call as isotropy. That is called, we mean that uniformity of direction. Uniformity of direction. What does that mean? Do you have a question? What does that mean, uniformity of direction? We can say space appears same from every direction. Space appears same from every direction. It appears same from every direction. There is no disagreement in the homogeneity of homogeneity of the direction. So basically, for every point in space, every direction in space, it remains constant. It remains same. It remains same. For example, universe will appear to you same from every direction. We call it as basically principle. Cosmological principle. Cosmological that says that universe appears to be same in all directions. In all directions. Here, isotropy means the uniformity of direction. In which direction you move in space, it is same. It is same. Are you getting my point? So this basically, this isotropy gives me conservation of angular momentum because it is related to direction. Conservation of angular momentum. It is related to conservation of angular momentum. So this uniformity of direction gives me conservation of angular momentum. See, angular momentum comes into play. It is r cross p is angular momentum. So basically, angular momentum comes into play whenever any body is having some sort of rotation. So when a body is having, see, one is momentum. Momentum is mass into velocity, the product of these two quantities. Mass into velocity. So you are moving in some direction, some linear direction. So the most quantity of motion possessed by a body in linear direction, you call it as linear momentum. You call it as linear momentum. But if you are having a motion, circular motion, something is rotating, something is curling or whirlpooling, in that case, you are having a torque. You are having a torque. Okay. So basically, it is an analog to this what you call the linear force. Analog to linear force. You are having torque R cross F. You are having torque R cross F. So basically, whenever you are having a rotating motion, you are having angular momentum there. You have angular momentum. So uniformity of direction gives me conservation of angular momentum. In every direction, for example, if we take a universe, it appears same. It appears same. So you call it as conservation, this uniformity of direction, and you call it as isotropy. You call it as isotropy. Then third thing is what you call as homogeneity of time. Homogeneity of time. Or we call it as uniformity of time. Uniformity of time. Uniformity of time. For example, you are performing some experiment. You are performing some experiment related to any field. Maybe some are here belong to zoology subject, some belong to some other fields, some belong to botany. You are performing any experiment. For example, in autumn, this is autumn. Okay, this is the fall. The season this time is fall. You are performing some experiment during this season, autumn. Okay, you are repeating the same experiment under same conditions in spring season. So your results should appear same. If your results are appearing same by performing the experiment in different seasons, and for example, an experiment is performed in 2023, today is the 31st of October. You repeat same experiment under same conditions next year, 31st October 2023. The experiment yields the same results. So you call it as homogeneity of time. Homogeneity of time. That means your time is not affecting the observations. Your time is not affecting the observation. That we call as uniformity of time. Time appears same. Time appears same. Shall I rub it here? So this was all about the conservation laws and the relation of these conservation laws with symmetries of nature. With symmetries of nature. Now we are on another topic: need for measurements. Need for measurements. Need for measurements. Need for measurements. So can I ask you a question? Can I ask you a question? why do we need measurements? Can anybody among you give answer to this question? Why do we need measurements?
Sir, for trade and market मतलब कुछ खरीदने के लिए या कुछ बेचने के
This is from you belong to the commerce subject. This is from commerce point of view. So why do we measurement? Why do we need measurements? We are basically, we are having physical quantities. I told you yesterday, physical quantities are those which can be quantified, which can be measured, So I told you all the velocity, force, acceleration, work, distance, displacement, all are physical quantities. To know the behavior of these physical quantities, you need measurement. That means measurement is very, very important for what? To study the behavior of physical quantities that are existing in this universe. See, we are also made up of some matter. We carry mass. We are having we do so many processes that involves energy. So these physical quantities, basically to have information, to find the behavior, we need measurements to give the precise information about the physical quantities. There was a statement given by Calvin, if I remember correctly. He says that what you can what you can measure and are speaking about, that means you know something about it. You know something about it. If you are speaking that thing which you cannot measure, that means you are having a meager knowledge about it. You don't know the things. When you express the things in numbers, that means you are able to comprehend the things. For example, when you know the Hubble Space Telescope, there was a well-known astronomer, Hubble. He has given the Hubble's law. You might have gone through in earlier classes. Okay? The universe is expanding. It is given by the Hubble's law, famous Hubble's law. So Hubble's law is basically equal to HR, which is basically universe. You are having H. H is one of the term in Hubble's law, Hubble constant. This is one of the physical quantity. So I say this physical quantity gives me the age of the universe. See, expansion started when the universe started expanding. When the Big Bang happened. When Big Bang took place, your space and time got its birth. So space and time got its birth or evolved when Big Bang happened. So from that point, your space is expanding. So in inverse of this Hubble's law gives me age of the universe. Because Hubble's law is something related to the velocity of precession of the galaxies. Are you getting my point? The expanding universe. I can say the expanding universe. So this physical quantity, if I can measure this physical quantity, so I can get what? I can get the age of the universe. So physical quantities basically give you, for example, you are having velocity of light. You say velocity of light is 3 × 10⁸ meters per second. So that means you are able to express this velocity of light in terms of numbers. Once you express anything in numbers, that means you are able to comprehend that thing. You are able to study the behavior of that thing. So you can compare velocity of light with velocity of sound, because you know the number value for the velocity of light. Okay? So you can then say whether the velocity of light, that means the photons are going faster, or I'm talking to you, is the velocity of the sound waves. So it is made of the rarefaction component, basically the longitudinal waves. So what I mean to say is that when you know that these physical quantities in terms of numbers, then you can make differentiate it with other physical quantities, or you can express laws in terms of these physical quantities. This is why we need to have measurements. Now, Now there are no, but measurements can be done. So we are having mass. Mass is one of the physical quantities. Mass is a physical quantity. It is again a physical quantity. That means amount of matter contained in some body. So mass means amount of matter contained in a body, or a body contained in a body. So mass is basically, if we try to find out the characteristics of mass, it is independent of size, it is independent of shape, and it is independent of conditions, or independent of some other body. Mass of this object is independent of the mass of this object. But this mass of two types. One is inertial mass, that is quantified in terms of the inertia. Then another is gravitational mass, which is due to the gravitational attraction of one body with respect to the other body. These are two types of masses. Now, how to make measurement of masses? What you look at? You are having unit system. So mass is measured in kilogram. It is measured in kilogram. Kilogram is in fact the SI unit of the mass as well. So what is a kilogram? Now the question arises, what is a kilogram? What is a kilogram? So the first definition of kilogram goes like this. You are having Earth. This is your pole of Earth. This is North Pole, for example. This is your equator. It is basically the distance, 1/10 millionth of the distance. 1/10 millionth of the distance from North Pole to equator. From North Pole to equator. This is meter. Again, I have. Okay. This is regarding meter. Okay. When we say mass is basically, we are having a 10⁻³ cubic centimeter of water at 4 degrees Celsius. 4 degree. This was the initial definition, first definition of this mass, this kg. Kg was considered as 10⁻³ centimeter of water at 4 degree centimeter. At 4 degree centimeter. But it has been modified. This definition of kg has been modified. It has been modified by. Now, what is the modern definition of this kg? It is basically we are having platinum iridium material cylinder at France International Bureau of Weights and Measures, if I remember correctly, that has been kept there, whose diameter and this 3.9 centimeters, if I remember correctly, with diameter and height of 3.9 centimeters. You are having some cylindrical shape which is made of platinum iridium. Why platinum iridium? That has been contained at what you call at 0 degrees Celsius or 273 Kelvin. Why at 1 bar of pressure? Why that has been kept under these conditions? So that it cannot expand with temperature, with heat. It cannot get affected by heat. So all the weight, all the kilogram samples that you are having here, they are basically the replica of those. A replica of this platinum iridium, in which platinum is, I guess, 90%. Iridium is 10%. This is a material made of which your kilogram is made. That has been kept under certain conditions so that it cannot expand. And this International Bureau of Weights and Measures in France, okay, that has been kept there. So all the kilograms that you have right now, they are basically the replica of this. Are you getting my point? So then you are having what you call the length. So how do you measure that? Length means the separation between 2 points. Separation between 2 points is a length. This is a scale here. This is a 1 meter scale here. Separation between these 2 points is length. Okay? But this length can be measured or quantified in terms of meters. in terms of meters. Now, what is a meter? As I was discussing earlier, you are having, this is your North Pole, the 1/10 millionth of distance from North Pole to equator. What is the distance from North Pole to equator? You take 1/10 millionth part of that, that is your 1 meter. This was the initial definition of meter. This was initial definition of meter was 1/10 millionth of distance from North Pole to, if you measure now distance from North Pole to the equator, North Pole to the equator. Now, what kind of definition we are having today? Usually, we are having a definition. One is again the platinum iridium rod that has been kept at Paris, France. So this rod was again kept under pressure 273 this Kelvin, okay, at 1 bar of pressure, because bar is the unit of pressure. 1 bar of pressure, ठीक है ना? So why it has been kept under such conditions? So that it should not expand, then the distance will get elongated, okay? So all the meters that you are having right now, whether in market or you use for measurements, they are replica of that rod. But actually, how meter has been defined? It has been defined. The meter has been defined. Basically, there is an atom that we call as krypton. Krypton atom. So we are having transition. That means when one electron jumps from one state to another state. See, electrons, you are having nucleus. So within the nucleus you are having some shells. When electron jumps from one state to another state, you call it as transition. You call it as transitions. Okay? If it is K, L, M. When electron jumps from K to L, you are having one transition. L to M, you are having another transition. So basically, the modern meter has been defined as, it is basically the wavelength. It is basically the wavelength produced by the transition between one level is, we call it 2p10 to 5d5. The transition between these two levels, the wavelength emitted by this atom, that between the transition 2p10 to 5d5 level. 5d5 level. What is the wavelength? You have any idea what is wavelength? So in wave motion, in your 9th class, earlier classes, you are having crusts and troughs. Okay? So the distance between these two, this is your lambda there. Between this and this point, this phase and this phase, you are having what you call the wave. Okay? So you are basically, whatever energy or transitions you are having in terms of waves. If I throw a pen, a wave is associated with this pen. So a wave will be having crusts and troughs. It will move like this. What is the distance between this point to this point? It is the wave. So when the transition takes place from 2p10 to 5d5 level of a krypton atom, so it defines the wavelength. And it is equal to, that is equal to 1 meter. So this is how the 1 meter has been defined. Or it is basic, or in other words, you can say path of length traveled in 1 by 3 into 10 raised power 8 meters in 1 second. You take this much of the factor meter 1 second. It may be some 0.00 something. That much of distance traveled in 1 second, you by distance traveled by light of this factor. 1 divided this factor. It is a very small factor. 0.000 something. In 1 second. That defines your 1 meter. This is how we have meter and the kg and the meter for the measurement of length and for the measurement of mass and length. I will stop today here, okay? I will not go further. ये करिए कौन सा ये आपका है ये मुझे सेंड करो बेटा